So I'm going to talk to you this morning about work we've done in ECOKNOWS on elicitation of stakeholder inputs in fisheries modelling. And I'm using stakeholder in a very broad sense here, not just a fisherman, but it could be anybody who knows anything about a stock. Like much of the work in ECOKNOWS, there's a broad group of us who've been involved in doing this. Okay, so in terms of the problem that we're dealing with, we know that various stakeholders have got information that's either direct knowledge or opinions on uncertainty that is likely to support the models for fisheries and hence move on to policy making. We also know that policymakers are more and more expected to be influenced by stakeholders and to draw on that knowledge. We need some way of getting the information out of stakeholders, both technical and commercial, industrial stakeholders and other interest groups. And in order to get that information, we need some sort of structure. We could just go along and ask people what they know, but in order to get it into an efficient, effective form, there needs to be some structure to the way that it's asked, and the more that structure can help to process and feedback to the people that are being elicited, the better. So what we're going to talk about here is the specific case of elicitation of inputs from stakeholder priors in Bayesian modeling. So we know exactly what kind of format we want the information, and what the task for us is to come up with a tool that transforms the knowledge that stakeholders have into an input into a Bayesian model. So the first thing then is to think about who's got the information, and so there's a good long list here. Where I talk about getting stakeholder knowledge, it's not necessarily just talking about going and interviewing an expert or a fisherman. It could be extracting information from literature, from other sources, records, and then transforming that kind of information and that sort of uncertainty also into the information you need for the priors for a Bayesian model. So what we need is a tool that will allow us to take information from any source. And what are we actually trying to get? So what we're trying to get here are probability distributions of the parameters of assessment. And really two ways to do that. One is to elicit a set of quantiles, and as long as we have some assumption about the general shape, we can do this with quite a small number of estimates of quantiles, and it doesn't really matter which quantile as long as we've got some assumption about the shape. And that may be a fairly big assumption at times, but it's one that needs to be made. The other alternative is to have a measure of location and scale, so things means, standard deviations, and so on. So those are the two basic things we're trying to get out of people. Now, it's a problem of trying to get information from people, particularly in some cases subjective information. There's the problem of anchoring. People stick to numbers they first think of, to round numbers, to common numbers. So that can bias the result. There's an issue of independence of the expert opinion. If the expert opinion is heavily influenced by access to particular reports or to particular experience as opposed to the general breadth of experience. The interpretation is important because the way that you ask something can affect the kind of answers that people are expecting to be giving. And a key issue, and one that we'll illustrate later on in this talk, is the point of overconfidence in experts. So we're not only asking people to say something about, for instance, a mean, we're also asking them to say something about their confidence around that, the interval around that. And over again you see that experts underestimate that uncertainty range, which from a Bayesian point of view is not very good. So we have two examples of the way that we've approached this. The first one doesn't involve a particular tool. It's looking at the concept of eliciting knowledge, and it was done with two experts looking at catchability of Bothnian Sea herring. And we had them here with two experts who were asked to give their opinion on catchability at 3 densities. So the densities were specified in approximate terms, very low, medium and high density. They're asked to take into account the effect of schooling within those densities. And what that elicited was, in this first case, 6 priors, so 3 per expert, that correspond to the catchability at these different densities. And the result of those come out in these 2 curves for the 3 different densities. So blue is low, green is intermediate, red is high for expert 1 and expert 2. And you can see immediately that the classic issue here that the experts have got different opinions. They're pretty different in most respects. So expert 1 is less certain. Expert 2 expects higher catchability at higher densities, whereas it's the other way around for expert 1. And you then got the question of how do you deal with multiple experts. Now in this first example we're just looking at 2 experts. In the second example we go on to much larger numbers. But in order to think about how to deal with this, it's nice to start with 2. So, some of the things we learned from that initial exercise was that it was actually quite difficult for the people providing the expertise to answer the questions, because in this case, catchability is something that's not directly observable. So there's quite a lot of mental processing going on in terms of what's happening. Going back to more basic level observable quantities might make it easier for the experts. On the other hand, it might not give you what you want. Second point is that the experts didn't agree on the directional mechanism of density dependence in catchability. So it's not just the value is different, it's the whole concept is different, and that makes it much, much harder to get a consensus. You can agree to differ on the numbers is one thing, but to agree to differ on concepts is a bit harder. So to deal with that, Bayesian model averaging seemed to be the best way to approach it. And ultimately, if you had some additional information to judge the quality of the individual experts or the information that they had, you might be able to put some other weighting on that. And there have been various ways of suggesting this, years of experience, proximity to the issue, things like that in other fields have been used as weighting mechanisms, giving a respondent a test on some known values and seeing how close they are to those, another way to do it. In this case, we didn't have any way to differentiate the 2 experts, so we didn't do that. But it gave us an idea of how we might approach this. So the second example is now on a much bigger scale, and we realized that we would need to develop a standardized way of collecting information from a larger number of experts in this elicitation. So the case here is about hake in the Cyclades in Greece. And what we're trying to get are priors for Bayesian stock assessment. So we're looking at age and growth parameters, proxy values to estimate stock recruitment. So we've designed this in Excel, and it's aimed at producing the numbers, the parameter values that would go into the GPDM, or indeed could go into some other Bayesian model if necessary. We also wanted a system that would give some sort of visual feedback to the people doing the elicitation, so that they could see the shape of the numbers that they were and uncertainties that they were presenting. So it wasn't just abstract numbers, but that, as I was saying yesterday, this need to be able to see a picture of the distributions was important, especially if we're only asking for a couple of quantile points. You need to see what the implications of that are within the assumed shape. So that's what the tool is going to do, which I'll illustrate in a moment. And we had 44 total elicitations here from a number of people for different types of information for different numbers of species, but in total 44 elicitations. So this is now a much, much more substantial exercise than the initial one that I described. So the tool is a series of spreadsheet pages that set out variables that might be elicited, and not necessarily all of them would be, so the respondents would be able to give values for ones that they know about. And the information that they give is in the blue cells, so they're able to pick any quantile that they're comfortable with and give two values for the variable at those quantiles. And then as they do that, immediately it generates the curves on the right to give them the feedback. So, is that the sort of shape that I'm expecting? Now, the shapes are all the same here because this is a set of ones where we've assumed they're going to be log normal. While the shapes are very similar, the scales are completely different. So they can look at that and say, for other quantiles that they might have an opinion on, is it roughly in the right place? So those ones are some log normal ones. Here's just an illustration of other shapes that we had in there. And some different statistics called for in the case of different distribution shapes that might be relevant. So there are several pages of these potential parameters that could be elicited. And that can be done then over and over again for different species or different conditions. And what the tool then does is to take inputs that are put in, some from experts, some from the literature, and it transforms those into an output that shows values like you get here. So the pink ones are output values, and the blue ones allow you to check and see where things might be at particular points. And what that then does is generates a series of curves. The black ones, the median curve from the series of runs for a stock recruitment relationship. So again, you've got feedback coming in immediately to say the numbers that you put in, are they generating a range of outputs that you're comfortable with the expertise that you have.
3 minutes.
Okay. And the final output then are the values that are needed to go into the GPDM. Okay, so challenges here. Well, expert overconfidence is an issue. Of course, another one is that when you're trying to validate the expertise, it may be that the data isn't sufficient. So we certainly came up with a case here in the Cyclades where it was hard to reconcile the expert opinions with estimates of initial stock size from 1950. So we're asking experts to estimate a stock size over 60 years ago, when none of them were around, and with records that weren't necessarily all that good. So data suggests the expert opinion was too small or too certain. On the other hand, you could say the expert opinion suggests that the data wasn't very good. So what do we do about that? Well, one of the nice things about a tool like this is if you get a problem like this that's difficult to reconcile, you can test it. So we can do, in effect, a sensitivity analysis here on the inputs. So here's a case here of the initial population size. The values up on the top here are what the expert said, or an example of what an expert said. And we can say, okay, well, let's assume that the experts are being too confident. We can increase the range of the quantiles and see what difference it makes. So if we made them considerably less certain here, so taking the 95th quantile up from 15 to 50, not much you can do with the lower quantile in this case because it's already pretty low. What that does is shift the whole distribution, and that sort of difference in uncertainty, in this case, would move the optimal catch median up from 230,000 to 430,000 fish. So you see it's quite sensitive to that degree of confidence that the experts have. A good case for having quite a lot of experts, but also a case for doing sensitivity analysis. So in summary, we've got a way to get stakeholder input, whether it's from individuals or from the literature. It's consistent in format and it catalogues the values, and indeed there are comment boxes off to the side that, where an elicitor can make notes about why somebody said something, if there's any reference to the data and so on. The graphical tools allow us to visualize what's going on or give feedback, immediate feedback to the people making the estimates. And the biggest obstacles we encountered, well, the reliability of knowledge about unobservable quantities is always a problem. On the other hand, at least we're collecting it in a consistent way and recording it, cataloging it. So if it's biased, at least it's consistently biased. The disagreement amongst experts, well, yeah, again, at least it's consistent, and we can then figure out how to deal with it. And you know, is it a case of overconfidence here? Should we plan on overconfidence and build a function in for that? So a tool that works out of ECOKNOWS. Thank you.